Welcome to this high-yield explainer on geomorphology. Now, if you're gearing up for the UPSC exams, you already know this topic is absolutely foundational. Today, we're going to decode the epic ongoing battle between Earth's internal builders, the fiery engines deep underground, and the external sculptors like wind, water, and ice that constantly wear the surface down. We've distilled all the essential data you need, so let's get right into it. Here's our roadmap for this session. We'll start deep underground with the internal engine and plate tectonics, then track India's incredible journey. After that, we'll cover sudden forces like earthquakes and volcanoes, examine exogenic landforms and soils, and finally wrap up by tackling some crucial previous year questions. Section 1. Earth's internal engine.
Geomorphology is the study of Earth's surface features and the processes, both endogenic, internal, and exogenic, external, that continuously shape them. Endogenic forces like tectonism and volcanism build relief, they uplift and create landforms. Exogenic forces like weathering and erosion work to level it, they wear down and flatten landforms. Together, they maintain a dynamic equilibrium on Earth's surface. Tectonic theories. The Earth's surface is dynamic. The understanding of how continents and oceans are arranged has evolved over time from the early drift hypothesis to the modern plate tectonics model. Let's go through each theory one by one. Continental Drift Theory, CDT. Proponent Alfred Wegener, 1912. Core hypothesis. All the continents were once a single supercontinent called Pangaea, meaning all Earth. It was surrounded by a megaocean called Panthalassa, meaning all water. Around 200 million years ago, Pangaea broke into two large landmasses. Laurasia in the north, Gondwanland in the south. They were separated by the Tethys Sea. Forces Wegener proposed for drift. Pole-fleeing force, centrifugal force due to Earth's rotation, caused by the equatorial bulge. Tidal force, gravitational pull of the sun and moon. Critique, these forces are mathematically too weak to move entire continents. This was the biggest weakness of Wegener's theory. He had the right idea but could not explain the mechanism. Evidence for continental drift theory. 1. Jigsaw fit. The coastlines of Africa and South America fit together remarkably well like puzzle pieces. This was the first clue. 2. Geological similarity. Rock belts that are 2000 million years old on the coast of Brazil match those found in West Africa in age and chemical composition. Rocks don't lie. 3. Tillite, glacial evidence. Glacial sedimentary rocks called tillite found in India have direct counterparts in 6 other landmasses of the southern hemisphere: Africa, South America, Antarctica, Australia, Madagascar, and the Falkland Islands. This proves these landmasses were once connected and in a polar region. 4. Placer deposits. Gold deposits found in Ghana, Africa, are derived from source veins in Brazil, South America, when the two continents lay side by side. 5. Fossil records. Identical species found across oceans. Mesosaurus, a freshwater reptile found in both Brazil and Africa. Glossopteris flora, a plant fossil found across all Gondwana landmasses. Lemurs found in India, Madagascar, and Africa, called Lemuria. B. Convection current theory and paleomagnetism. Proponent Arthur Holmes, 1930s. Core hypothesis. Radioactive decay in the mantle creates thermal differences, which drive convection cells in the mantle. These convection currents provided the missing force that Wegener could not explain. Hot material rises, spreads sideways, drags the crust with it, then sinks, creating a conveyor belt effect. C. Seafloor spreading theory. Proponent Harry Hess, 1961. Core hypothesis. Volcanic eruptions at mid-oceanic ridges, moors, create new basaltic crust. The ocean floor acts as a conveyor belt, pushing older crust toward deep-sea trenches where it subducts and is consumed. Supporting facts. Rocks equidistant from the ridge crest show similarities in age and chemical composition. Rocks closer to the ridge are youngest, age increases moving away. Ocean floor sediment layers are unexpectedly thin, this means the ocean floor is of recent formation. Oceanic crust is much younger, less than 200 million years old, than continental crust, around 3,200 million years old. Seismicity, shallow earthquakes at moors, deep-seated quakes at trenches. Paleomagnetism. Earth's magnetic field gets recorded in basaltic oceanic crust as iron-rich minerals align with the magnetic field when lava cools. This creates a symmetrical magnetic stripping, alternating normal and reversed polarity on either side of mid-oceanic ridges. This is proof of geomagnetic reversal every few 100,000 years and proof that new crust is continuously being added at moors.
Section 2. Plate tectonics and India's girdle.
D. Plate tectonics theory. Proponents Mackenzie, Parker, and Morgan, 1967. Core concept. Plate tectonics combines continental drift plus seafloor spreading plus subduction into one unified theory. The lithosphere, crust plus upper mantle, 5 to 200 km thick, is broken into rigid plates floating on the semi-fluid asthenosphere. Movement is driven by convection currents in the mantle. Major plates, 7. Antarctica, North American, South American, Pacific, India, Australia, New Zealand, African, and Eurasian. Key minor plates. Cocos, Central America, Pacific, Nazca, South America, Pacific, Arabian, Philippine, Caroline, Philippine, Indian. Plate boundary interactions. 1. Divergent boundary, constructive. Plates pull apart, new crust is generated site of seafloor spreading. Example, Mid-Atlantic Ridge. 2. Convergent boundary, destructive. Plates collide, one subducts, crust is destroyed at a subduction zone. 3 types. Ocean-ocean convergence, island arcs form. Example, Japan. Ocean-continent convergence, volcanic mountains form. Example, Andes. Continent-continent convergence, fold mountains form, no subduction of lighter continental crust, hence broad folding. Example, Himalayas. 3. Transform boundary, conservative. Plates slide horizontally past each other. Crust is neither created nor destroyed. Example, San Andreas Fault in California. Movement of the Indian plate. This is extremely important for UPSC, especially for questions about the Himalayas and Indian geography. Early position. Around 225 million years ago, the Indian plate was part of Gondwanland attached to Australia, Antarctica, Africa, and Madagascar. The Tethys Sea lay to its north. Journey. India separated from Gondwanland around 130 to 140 million years ago, MYA, and began moving northward rapidly. It collided with the Eurasia Plate around 55 to 50 MYA, causing the Tethys Sea to close and the Himalayas to rise. Current movement. India is still moving northeast at approximately 5 centimeters per year. This pushes the Himalayas higher and causes frequent earthquakes in the Himalayan region. Boundaries of the Indian plate. Northern boundary, continent-continent convergence, Himalayas. Southern boundary, divergent boundary with Antarctic plate, Indian Ocean ridge. Eastern boundary, subduction zone, Java Trench, plus convergence with Burmese plate, Arakan Yoma. Western boundary, transform boundary with Arabian plate along the Owen fracture zone, Makran coast offshore. Geomorphic processes. The endogenic and exogenic forces that cause physical stresses and chemical actions on Earth materials bringing about changes in the Earth's surface configuration are called geomorphic processes. Now let's compare endogenic and exogenic forces. First, based on their origin, endogenic forces originate deep within the Earth's interior, whereas exogenic forces operate at or near the Earth's surface. The driving force behind endogenic processes is the Earth's internal heat, generated mainly by radioactive decay and the primordial heat left over from the formation of the planet. In contrast, exogenic processes derive their energy from solar radiation and the force of gravity. In terms of their nature, endogenic forces are land-building forces. They uplift, fold, fault, and deform the Earth's crust, creating mountains, plateaus, and other major landforms. Exogenic forces, on the other hand, are land-wearing forces. Through weathering, erosion, transportation, and deposition, they gradually wear down and reshape the land. There is also a difference in their speed of operation. Endogenic forces may act very slowly over millions of years, as seen in mountain-building movements, or they may act suddenly and violently in the form of earthquakes and volcanic eruptions. Exogenic forces are generally slow and continuous, constantly modifying the Earth's surface over long periods of time. So remember this simple idea: endogenic forces build the Earth's relief, while exogenic forces continuously wear it down and remodel it. Endogenic forces. Endogenic processes are divided into 1. Slow movements, diastrophism. Gradual processes lasting thousands of years, deforming the crust through folding or fracturing. Orogenic processes, mountain building through severe folding, operate in a horizontal manner. Example, Himalayas, Alps. Epeirogenic processes, continental building through uplift or warping of large parts of the crust, simple deformation, operate in a vertical manner. 2. Sudden movements. Occur mostly at lithospheric plate margins, highly unstable regions. Examples, volcanism and earthquakes cause rapid changes in contours, river courses, and shorelines.
Section 3. Earthquakes and volcanic activity.
B. Earthquakes and seismology. Meaning, sudden shaking of Earth's crust due to rapid release of accumulated energy along faults. Energy is released in the form of seismic waves. Mechanism: energy releases along a fault, a sharp break in crustal rocks. Rocks slide past one another, overcome friction, and release energy abruptly. Focus: hypocenter, the point inside the Earth where the earthquake originates. Epicenter, the point on Earth's surface directly vertically above the focus. It is the first point to experience the waves. Types of earthquakes. Tectonic earthquake, due to fault movements along tectonic plates, most common. Volcanic earthquake, linked to active volcanic activity. Collapse earthquake, cave-ins in underground mines. Explosion earthquake, from chemical or nuclear blasts. Reservoir induced, due to pressure from large dams. Seismic waves. Body waves, generated at the focus, travel through Earth's interior. P waves, primary. Longitudinal waves, like sound waves. Particles vibrate parallel, to and fro, to the direction of wave propagation. Fastest waves, first to arrive at the surface, recorded earlier than S waves. Travel through gaseous, liquid, and solid materials. S waves, secondary. Transverse waves. Particles vibrate perpendicular, up and down, at right angles to wave direction. Slower than P waves. Travel only through solids. This property proved that the outer core is liquid because S waves disappear beyond 105 degrees. Surface waves travel along Earth's surface. Slowest waves but cause maximum destruction. Tides, love waves, fastest surface waves, slower than body waves, and Rayleigh waves, slowest of all. Seismic shadow zones. Areas that do not receive direct seismic waves, due to refraction or absorption by Earth's core. P-wave shadow zone, 105 degrees to 145 degrees, refraction at the liquid outer core. S-wave shadow zone, beyond 105 degrees, S-waves cannot pass through the liquid core at all. The shadow zone of S-waves is larger than P-waves, covering roughly 40% of Earth's surface. Measurement scales. Richter scale measures magnitude, energy released. Logarithmic, an increase of 1 unit equals a 10-fold increase in wave amplitude. Ranges from 0 to 10. Mercalli scale measures intensity, visible damage effect. Ranges from 1, not felt, to 12, total destruction. Global distribution of earthquakes. Circum-Pacific Belt, Ring of Fire tilde 68, 70% of all earthquakes overlaps with major volcanic zones. Alpine Himalayan Belt, tilde 15, 20% of quakes, continent-continent collision earthquakes. Mid-oceanic ridges, sites of frequent, shallow focus earthquakes due to tensional forces. Volcanism. Volcanism is a sudden endogenic geomorphic process involving the movement of molten rock, magma, onto or toward the Earth's surface through crustal vents or fissures. Primarily driven by mantle convection currents generated by radioactive decay and primordial heat. Material that reaches the ground includes lava flows, pyroclastic debris, volcanic bombs, ash and dust, and gases such as nitrogen compounds, sulfur compounds, minor amounts of chlorine, hydrogen, and argon. Before we understand different types of volcanoes, we must first understand the nature of magma because the type of magma largely determines the type of volcanic eruption. Broadly, magma can be classified into two types, acidic or felsic magma, and basic or mafic magma. Acidic magma contains a very high percentage of silica, generally more than 65%. Due to this high silica content, it becomes highly viscous or thick and does not flow easily. It is lighter in color, less dense, and tends to trap large amounts of gases within it. As pressure builds up inside the volcano, eruptions become violent and explosive. These explosive eruptions usually form steep-sided volcanic mountains known as stratovolcanoes or composite volcanoes. In contrast, basic or mafic magma contains a lower silica content, usually between 45 and 55%. It is much more fluid and flows easily. It is darker in color, denser, and allows gases to escape more freely. As a result, eruptions are generally quiet and non-explosive, with lava flowing smoothly over large areas. Such eruptions often create broad volcanoes with gentle slopes known as shield volcanoes. Now let's look at the major types of volcanoes. The first type is the shield volcano. These are the largest volcanoes on Earth and are characterized by very gentle slopes. Since they are formed by highly fluid basaltic lava, the lava spreads over large distances before cooling. A classic example is Mauna Loa in Hawaii. The second type is the composite or stratovolcano. These volcanoes have steep sides and are formed by alternating layers of lava and pyroclastic material. Because the lava is more viscous, eruptions tend to be explosive. Famous examples include Mount Fuji in Japan and Mount Vesuvius in Italy. The third type is the caldera volcano. These are among the most explosive volcanic systems. During a massive eruption, the magma chamber beneath the volcano empties rapidly, causing the volcanic structure to collapse inward and form a large depression called a caldera. Yellowstone in the United States and Lake Toba in Indonesia are famous examples. Another important volcanic feature is the flood basalt province. Here, extremely fluid basaltic lava erupts through long cracks in the Earth's crust and spreads across vast areas, creating extensive lava plateaus. The Deccan Traps of India and the Siberian Traps of Russia are classic examples. We also have mid-ocean ridge volcanoes. These occur along the world's longest mountain chain, stretching for nearly 70,000 kilometers across the ocean floor. Basaltic magma continuously rises here as tectonic plates move apart. The East Pacific Rise is a well-known example. Finally, there are cinder cone volcanoes. These are relatively small, steep-sided volcanoes formed mainly from volcanic fragments and ash known as tephra. They are usually short-lived and develop around a single vent. Parachuting in Mexico is one of the most famous examples. So remember this simple connection: high silica magma leads to explosive eruptions and steep volcanoes, while low silica magma leads to gentle eruptions and broad volcanoes. Intrusive volcanic landforms. Magma that solidifies below the surface. Batholiths, massive granitic bodies, cooled deep magma chambers. Laccoliths, dome-shaped, level base, pipe-like conduit. Lapoliths, saucer-shaped, concave up. Phacoliths, wavy masses at syncline base, anticline top. Sills sheets, horizontal tabular bodies, sheets is equal to thinner sills. Dikes, vertical walls, flood basalt feeders. Associated volcanic concepts. Mantle plumes, columns of hot rock rising from the core mantle boundary. Fixed stationary. Create volcanic chains in the middle of tectonic plates. Example: Hawaii, reunion. Mushroom-shaped long conduit, tail, connecting a bulbous, expanding head. Hotspots, volcanic regions above stationary mantle plumes, not at plate boundaries. As the plate moves over the fixed plume, it creates a time-progressive chain of islands, youngest over plume, oldest extinct, Gaiets, trail behind. Pyroclastics, fragmented volcanic ejecta, ash, lapilli, blocks, and bombs. Leher, destructive volcanic mudflow debris flow. Geothermal energy, tapping heat from magma hot water to generate electricity, clean and renewable. Geysers, underground water heated by volcanic heat steam expansion pressure builds explosive intermittent eruptions. Examples: Yellowstone, Iceland, New Zealand. Hot springs, continuous flow of heated water through wide vents, no pressure or eruptions. Contain dissolved minerals with medicinal value and colorful cyanobacteria. India, Surya Kund, Yamunotri, Manikaran, HP, Puga Valley, Ladakh, geothermal potential. Fumaroles solfataras, gas-only vents, steam plus SOCO HCl. Mark waning volcanism toward extinction. Solfatara, Naples, Italy, known as land of sulfur. Diatreme, a volcanic pipe or vent filled with breccia, fragmented rock, the neck of a volcano. Barren Islands, India's only active volcano, Andaman Sea, uninhabited stratovolcano. Formed by Indian plate subduction under Burmese plate. Caldera of Pleistocene explosive origin, eruptions, since 1787 dormancy active again 2005 to 10, 2013 to 14, 2017, 2022, September 2025, lava flows plus ash. Strombolian activity plus frequent gas ash emissions, recent cone growth of 50 m since 2005.
Section 4. Exogenic forces and landforms.
Exogenic forces. Exogenic forces are external land-wearing forces that originate at or near Earth's surface, drawing energy from the atmosphere and the sun. These processes work toward gradation, the wearing down of relief variations through degradation, wearing down, aggradation, filling up. All exogenic geomorphic processes are covered under the general term denudation. Driving forces. Solar energy, ultimate driver, controls weather, wind, precipitation, thermal gradients. Gravity activates downslope movements, causes stresses through overburden pressure, drives tides, currents, winds indirectly. Other factors, temperature and precipitation. A. Weathering. Weathering is the in situ disintegration of rocks, mechanical disintegration and chemical decomposition on site, with little to no motion of materials. 1. Physical, mechanical, weathering. Driven by applied forces like thermal expansion and pressure release. Unloading expansion, sheeting removal of overlying rock load causes expansion peeling of curved sheets exfoliation domes. Thermal expansion, diurnal heating and cooling cause expansion and contraction effective in dry climates high elevations granular disintegration. Frost wedging, water enters cracks, freezes, and expands, increasing volume, forcing rocks apart most effective in high elevations and mid-latitudes. Salt weathering, growth of salt crystals in rock pores exerts physical pressure granular disintegration highly effective in arid and coastal regions. 2. Chemical weathering. Rocks decompose or dissolve through chemical reactions involving water, air, and heat. Solution, simple dissolution of minerals in water or weak acids, nitrates and sulfates. Carbonation, rainwater absorbs atmospheric co-forms weak carbonic acid reacts with carbonate rocks like limestone dissolves them contributes to karst topography. Hydration, minerals take up water and expand creates physical stress and fatigue in the rock. Example, calcium sulfate plus water is equal to gypsum. Oxidation and reduction, oxidation involves addition of oxygen, rusting of iron. Reduction occurs in oxygen-poor, waterlogged environments changes rock color from red to greenish gray. 3. Biological weathering. Involves burrowing by organisms, earthworms, rodents, root pressure from plants and decaying organic matter producing humic acids. B. Mass wasting, mass movements. Transfer of rock debris down slopes under the direct influence of gravity. Unlike erosion, no geomorphic agent like running water or wind participates directly, gravity is the sole driver. Slow movements. 3. Extremely gradual displacement of soil or rock debris. Solifluction, slow downslope flow of water-saturated soil in periglacial, cold climates. Rapid movements. Earth flow, movement of water-saturated clay silt down hillsides. Mud flow, rapid flow of thick layers of saturated weathered material, often triggered by torrential rain. Landslides, rapid, perceptible movement of relatively dry materials along a sheer plain. Debris avalanche, faster than mud flows, occurring in narrow tracks on steep slopes. C. Erosion and deposition. Erosion, acquisition and transportation of rock debris by geomorphic agents, running water, groundwater, glaciers, wind, waves, driven by kinetic energy. Abrasion, erosion aided by the rock debris carried by these agents. Deposition, a consequence of erosion, occurs when agents lose velocity energy. Coarser materials deposit first. Landforms and their evolution. A. Running water, fluvial landforms. Stages of river development. Youth stage, steep gradient, V-shaped valleys, waterfalls and rapids, no floodplains. Mature stage, wider valleys, meanders develop, floodplains begin. Old stage, gentle slope, broad floodplains, oxbow lakes, natural levees. Erosional landforms. Valleys, rills, gullies, valleys. Gorge, steep, straight sides, same width top and bottom, hard rocks. Canyon, step-like sides, wider at top, sedimentary rocks. Potholes, circular depressions, formed by abrasion, large ones at waterfalls. Plunge pools. Incised meanders, deep meanders cut in hard rock due to vertical erosion. River terraces, step-like benches, old floodplain levels. Paired same height, unpaired different heights. Depositional landforms. Alluvial fans, cone-shaped deposits at foothills, coarse, unsorted material. Deltas, triangular deposits at river mouth, well-sorted, stratified sediments. Floodplains, flat depositional surfaces. Active current deposition, inactive higher older level. Natural levees, raised ridges along river banks, coarse deposits. Point bars, deposits on inner, convex, side of meanders. Braided channels, multiple small channels, high load, low velocity. Now let's understand the complete journey of a river from its origin to its mouth through this single diagram. The river begins in the mountains with a steep gradient, where vertical erosion is dominant. Small rills merge into gullies, which further deepen to form V-shaped valleys. Continued erosion creates gorges in hard rocks and canyons in horizontally layered sedimentary rocks. At waterfalls, the constant abrasion by rock fragments excavates potholes and eventually forms a deep plunge pool. As the river continues to cut vertically, winding bends become deeply entrenched, producing incised meanders, while former floodplain levels remain as river terraces, which may be paired or unpaired. As the gradient decreases, the river enters its mature stage. Here, lateral erosion becomes dominant, and the river starts developing broad meanders. Sediments are deposited on the inner bends to form point bars, while repeated flooding builds natural levees along the banks. At the foothills, rivers lose energy and deposit coarse sediments, forming alluvial fans. Further downstream, extensive deposition creates wide floodplains, and where sediment load is high with relatively low velocity, the river splits into multiple braided channels. Finally, when the river enters the sea or a lake, its velocity drops sharply, leading to the formation of a delta composed of well-sorted and stratified sediments. This single diagram beautifully summarizes the entire fluvial cycle, from dominant erosion in the upper course to dominant deposition in the lower course, and is one of the most important concepts for UPSC geography. The groundwater karst topography. Formed in regions with limestone or soluble rocks through carbonation, chemical weathering by carbonic acid. Erosional features. Swallow holes, small circular openings, water disappears underground. Sinkholes, funnel-shaped depressions. Solution type dissolution, collapse type, dolines, roof collapse. Ubalas, large depressions, formed by merging sinkholes. Lapis, grooved, rough limestone surface. Caves, underground cavities, form along bedding planes, open at both ends tunnels. Depositional features. Stalactites, hang from ceiling, taper downward. Stalagmites, rise from cave floor. Pillars, formed when stalactite and stalagmite join. C. Glaciers, glacial landforms. Erosional features. Cirque, ball-shaped hollow at mountain head, water-filled tarn. Horn, sharp pyramidal peak, formed by 3 or more cirques eroding back. Arete, sharp ridge between 2 cirques. Glacial valley, U-shaped, broad floor, steep sides. Hanging valley, smaller valley above main valley, forms waterfalls. Fjord, deep glacial valley filled with seawater. Depositional features. Moraines, ridges of unsorted debris, till. Terminal end, lateral sides, medial center, ground valley floor. Eskers, long winding ridges, deposited by subglacial streams. Drumlins, oval hill. Blunt end faces glacier, tail points flow direction. Outwash plains, stratified sand and gravel, deposited by meltwater. D. Waves and currents, coastal landforms. Erosional features. Cliffs, steep rock faces, formed by wave erosion. Wavecut platforms, flat surfaces at cliff base. Sea caves, hollow openings in cliffs. Stacks, isolated rock pillars, remnants of collapsed arches. Depositional features. Beaches, sand pebble deposits, temporary accumulation. Bars, sand ridges parallel to coast, exposed barrier bars. Spits, sand bar attached at one end, projects into sea. Lagoons, water body enclosed by bar spit. Example, Chilika Lake. Wind, Aeolian landforms. Erosional features. Pediments, gently sloping rocky floors at mountain base. Pediplains, broad flat plains formed by merging pediments. Playas, temporary desert lakes, salt-covered alkali flats. Deflation hollows, depressions formed by wind removing loose soil. Mushroom rocks, narrow base, broad top, shaped by abrasion. Zeugen, hard rock top, soft base eroded. Yardans, long narrow ridges aligned with wind direction. Depositional features. Birchen dunes, crescent-shaped, horns point away from wind. Parabolic dunes, crescent reversed, horns point toward wind. Scythe dunes, long narrow ridge, single wing. Longitudinal dunes, parallel to wind direction. Transverse dunes, perpendicular to wind direction. Now, before we move on to the next topic, let's quickly revise all the geomorphic landforms we've discussed. Pause the video for a few seconds, go through this complete chart, and try to recall each landform along with the geomorphic agent responsible for its formation.
Section 5. Rocks and Soil Formation.
Now, soil formation, pedogenesis. Process of soil formation. Weathering mantle. Weathering provides parent material, regolith. Colonization. Pioneer species, lichens, mosses, colonize debris. Humus accumulation. Decomposition adds organic matter. Maturation. Vertical differentiation into A, B, C horizons. Mature soil profile. Soil forming factors. Parent material, passive determines texture, mineral composition, color. Climate, active moisture controls chemical biological activity, temperature accelerates reactions. Biological activity, active adds humus, nitrogen. Fixation enriches soil. Topography, passive influences drainage and erosion, thin soils on slopes, thick on plains. Time, passive controls maturity and profile thickness. Rock system. Rocks are naturally occurring solid aggregates of one or more minerals. They act as the physical record of geomorphic processes. They are grouped into three major types, igneous, sedimentary, and metamorphic. 1. Igneous rocks, primary. Formation, cooling and solidification of magma, interior, or lava surface. Features, hard, durable, usually impermeable, and non-fossiliferous, fossils are destroyed by heat. Types by formation. Intrusive, plutonic form below surface, slow cooling, coarse crystals. Example, granite. Extrusive, volcanic form on surface, rapid cooling, fine crystals. Example, basalt. Types by silica content. Felsic, acidic high silica, greater than 65%, light color, less dense. Examples, granite, rhyolite. Mafic, basic low silica, tilde 45-55%, dark color, more dense. Examples, basalt, gabbro. Ultramafic, very low silica. Less than 45%. Example, peridotite. Sedimentary rocks. Formation, accumulation, compaction, and cementation, also called lithification of sediments derived from weathering and erosion. Features, layered or stratified, fossiliferous, meaning they contain fossils, and generally porous and permeable. Types. Clastic or detrital, formed from rock fragments. Examples, sandstone, shale, and clay. Chemical, formed by evaporation or precipitation. Examples, rock salt and gypsum. Organic or biogenic, formed from plant and animal remains. Examples, limestone, coal, and chalk. Important notes. Chalk, with the chemical formula calcium carbonate, is a soft sedimentary rock. It is highly porous, meaning it contains many pores that can absorb water, and it is also permeable because the pores are well connected, allowing water to flow easily. Clay consists of very fine, tightly packed particles with tiny pores. Water moves through it very slowly, so clay retains water. It is porous but nearly impermeable. Metamorphic rocks. Formation, metamorphic rocks are formed by the alteration of existing igneous, sedimentary, or older metamorphic rocks under extreme changes in pressure, volume, and heat. Structure, they commonly show foliation, lineation, or banding. Types of metamorphism. Dynamic metamorphism, mechanical breaking due to stress without any chemical change. Thermal or contact metamorphism, alteration caused by heat from intruding magma. Regional metamorphism, large-scale alteration caused by tectonic mountain building processes. India's rock systems. Archean rock system. The oldest basement rocks of India. These rocks belong to the Precambrian period and are about 4 billion years old. They are unfossiliferous and highly crystalline. They include gneisses and schists, which are crystalline metamorphic rocks. The Dharwar system consists of older metamorphosed sedimentary rocks rich in iron ore, manganese, copper, lead, and gold. They are economically significant but do not contain fossil fuels. Purana rock system. An ancient sedimentary belt formed between 1,400 million and 600 million years ago. The Kudappa system contains fossil-poor basin folds with black shales, sandstones, and limestones. It is rich in iron, manganese, copper, nickel, cobalt, and cement-grade limestone. The best exposures are found in Kudappa, Andhra Pradesh. The Vindhya system is a thick unfossiliferous sedimentary sequence, approximately 4,000 meters thick, resting over the Archean base. It contains durable building stones, limestone, glass sand, and diamonds found at Panna and Golconda. Dravidian rock system. Formed between 600 million and 300 million years ago. These rocks are mainly found in the extrapeninsular region, especially the Himalayas and the Ganga plains. They contain limestones, shales, quartzites, and fossils, representing the early stage of coal formation globally, although most Indian coal is younger. Aryan rock system. Formed from the late Paleozoic period to recent times. The Gondwana system, dating from the Permian and Triassic to the Mesozoic era, contains sedimentary deposits and about 98% of India's coal reserves. It also contains iron ore, copper, uranium, sandstones, slates, and conglomerates. The Jurassic system includes marine transgression deposits with coral limestone found in Rajasthan and Kutch. The Deccan Trap, formed during the late Cretaceous to early Paleogene, consists of extensive basaltic lava flows across Maharashtra, Saurashtra, Malwa, and Karnataka. Weathering of these rocks produces black cotton soil, also known as Reger soil. The Tertiary and Quaternary rocks are associated with oil and petroleum deposits and represent major geological events such as the rise of the Himalayas. Now let's solve all the previous year questions from this chapter. I'll read the question, read all options, give you a moment to think, and then explain the answer in short. Question 1, UPSC Prelims 2025. Which of the following are evidences of the phenomenon of continental drift? I. The belt of ancient rocks from Brazil coast matches with those from Western Africa. 2. The gold deposits of Ghana are derived from the Brazil Plateau when the two continents lay side by side. 3. The Gondwana system of sediments from India is known to have its counterparts in 6 different landmasses of the southern hemisphere. Option A, I and 3 only. Option B, I and 2 only. Option C, I, 2 and 3. Option D, 2 and 3 only. Pause 8 seconds. Answer, option C, I, 2 and 3. Statement I true. 2,000-million-year-old rock belts in Brazil match those in West Africa. Geological similarity is direct evidence of CDT. Statement 2 true. Gold in Ghana, Africa, is derived from source veins in Brazil, South America. This is the placer deposits evidence. Statement 3 true. Gondwana tillite sediments from India have counterparts in 6 southern hemisphere landmasses: Africa, South America, Antarctica, Australia, Madagascar, Falkland Islands. Heavy check mark. All 3 are valid evidences. Answer C. Question 2, UPSC Prelims 2014. Which of the following phenomena might have influenced the evolution of organisms? Continental drift. Glacial cycles. Option A, 1 only. Option B, 2 only. Option C, both 1 and 2. Option D, neither 1 nor 2. Pause 8 seconds. Answer, option C, both 1 and 2. Continental drift separated landmasses, isolated species, and caused divergent evolution. It directly influenced which organisms lived where and how they evolved. Glacial cycles caused mass extinctions and survival pressure, forcing organisms to adapt to cold, migrate, or perish. This shaped evolution profoundly. Both influenced evolution. Answer C. Question 3, UPSC Prelims 2023. Consider the following statements. Statement 1, in a seismograph, P waves are recorded earlier than S waves. Statement 2. In P waves, individual particles vibrate to and fro in the direction of wave propagation, whereas in S waves, the particles vibrate up and down at right angles to the direction of wave propagation. Option A, 1 only. Option B, 2 only. Option C, both 1 and 2. Option D, neither 1 nor 2. Pause 8 seconds. Answer, option C, both 1 and 2. Statement 1 true. P waves are the fastest seismic waves, they always arrive at the seismograph before S waves. Statement 2 true. P waves are longitudinal, particles move to and fro parallel to wave direction. S waves are transverse, particles move up and down at right angles to wave direction. Answer C. Question 4 UPSC Prelims 2024. Consider the following. Pyroclastic debris. Ash and dust. Nitrogen compounds. Sulfur compounds. How many of the above are products of volcanic eruptions? Option A, only 1. Option B, only 2. Option C, only 3. Option D, all 4. Pause 8 seconds. Answer, option D, all 4. Volcanic eruptions produce lava flows, pyroclastic debris, 1. Ash and dust, 2. Volcanic bombs and gases including nitrogen compounds, 3. Sulfur compounds, 4. Chlorine, hydrogen and argon. All 4 are confirmed products of volcanic eruptions. Answer D. Question 5 UPSC Prelims 2024. Consider the following statements. Statement I. Rainfall is one of the reasons for weathering of rocks. Statement 2. Rainwater contains carbon dioxide in solution. Statement 3. Rainwater contains atmospheric oxygen. Which one of the following is correct? Option A. Both 2 and 3 are correct and both explain statement I. Option B. Both 2 and 3 are correct, but only one of them explains statement I. Option C. Only one of 2 and 3 is correct and that explains statement I. Option D. Neither 2 nor 3 is correct. Answer, option A. Both 2 and 3 are correct and both explain statement I. Statement 2 true. Rainwater absorbs atmospheric co-forms carbonic acid causes carbonation weathering of carbonate rocks. Explains statement I. Statement 3 true. Rainwater also contains dissolved atmospheric oxygen causes oxidation weathering, rusting of iron in rocks. Explains statement I. Both are correct and both explain why rainfall weathers rocks. Answer A. Question 6 UPSC Prelims 2021. In the case of which one of the following biogeochemical cycles is the weathering of rocks the main source of release of nutrient to enter the cycle? Option A. Carbon cycle. Option B. Nitrogen cycle. Option C. Phosphorus cycle. Option D. Sulfur cycle. Pause 8 seconds. Option C. Phosphorus cycle. Unlike carbon from atmosphere CO and nitrogen from atmosphere N, phosphorus has no atmospheric reservoir. It enters the cycle only through the weathering of phosphate-bearing rocks like apatite. Rock weathering is the primary and main source of phosphorus for all living systems. Answer C. Question 7 UPSC Prelims 2013. Which of the following are responsible for bringing dynamic changes on the surface of the Earth? Electromagnetic radiation. Geothermal energy. Gravitational force. Plate movements. Rotation of the Earth. Revolution of the Earth. Option A 1, 2, 3 and 4 only. Option B 1, 3, 5 and 6 only. Option C 2, 4, 5 and 6 only. Option D 1, 2, 3, 4, 5 and 6. Pause 8 seconds. Answer, option D 1, 2, 3, 4, 5 and 6. All 6 are responsible for dynamic changes on Earth's surface. Electromagnetic radiation drives exogenic processes, solar energy. Geothermal energy drives endogenic processes, radioactivity, primordial heat. Gravitational force mass wasting, tides, erosion. Plate movements earthquakes, volcanism, mountain building. Rotation Coriolis force, tides, winds, currents. Revolution seasons, climate variation. All 6 are listed as factors responsible for dynamic changes. Answer D. Question 8 UPSC Prelims 2022. Gandikota Canyon of South India was created by which one of the following rivers? Option A. Kaveri. Option B. Manjira. Option C. Pennar. Option D. Tungabhadra. Pause 8 seconds. Answer, option C, Pennar. Gandikota is known as the Grand Canyon of India, located in Kadapa district, Andhra Pradesh. It was carved by the Pennar River, also spelled Penneru, flowing through the Ramala Hills. Answer C. Question 9, UPSC Prelims 2025. Consider the following statements. Statement I, in the context of the effect of water on rocks, chalk is known as a very permeable rock whereas clay is known as quite an impermeable or least permeable rock. Statement 2, chalk is porous and hence can absorb water. Statement 3, clay is not at all porous. Which one of the following is correct? Option A, both 2 and 3 are correct and both explain statement I. Option B, both 2 and 3 are correct but only one explains statement I. Option C, only one of 2 and 3 is correct and that explains statement I. Option D, neither 2 nor 3 is correct. Pause 8 seconds. Answer, option C, only one of 2 and 3 is correct and that explains statement I. Statement 2, true. Chalk is highly porous, it has many interconnected pores, which allows it to absorb and transmit water. This explains why chalk is permeable. Explains statement I. Statement 3, false. Clay is porous, it has many tiny pores. However, clay pores are so extremely small and tightly packed that water movement is nearly impossible. Clay is porous but nearly impermeable. Saying clay is not at all porous is wrong. Only statement 2 is correct and explains statement I. Answer C. Question 10, UPSC Prelims 2013. Consider the following statements. Natural gas occurs in the Gondwana beds. Mica occurs in abundance in Koderma. Dharwars are famous for petroleum. Which of the statements given above are correct? Option A, 1 and 2. Option B, 2 only. Option C, 2 and 3. Option D, none. Pause 8 seconds. Answer, option B, 2 only. Statement 1, false. Gondwana beds are famous for coal, approximately 98% of India's coal. Natural gas is associated with tertiary and quaternary rocks, not Gondwana beds. Statement 2, true. Koderma in Jharkhand is the mica capital of India, known for high-quality sheet mica production. Statement 3, false. Dharwars are metamorphosed sedimentary rocks known for iron ore, manganese, copper, lead, and gold, not petroleum. Petroleum is associated with tertiary rocks. Answer B. And that's a complete wrap on Chapter 3, Geomorphology. We covered tectonic theories, plate tectonics, the Indian plate's journey, endogenic and exogenic forces, earthquakes and seismic waves, volcanism, all types of landforms, weathering, mass wasting, soil formation, rock systems, India's rock systems, and solved 10 previous year questions from 2013 to 2025. If this video helped you, please like it, share it with your fellow aspirants, and subscribe so you don't miss the upcoming chapters. Drop a comment below with the concept you found most interesting today.